All right, in this lesson, we're going to look at different strategies for integration. So I've listed some of the things that you can do. And then if you remember back from basic integration, we had our kind of our flow chart for what to use when we're doing integration. So you may want to pull this out because I'm going to reference this. And of course, we want our advanced integration formulas sheet out as well, because we're going to use both of those. So we're not learning anything new today. All of this is going to be a review of what we've done, but what makes it difficult is the fact that I'm not telling you what technique to use, so you're having to identify what technique to use and how to work the integral. So on this first one, we have the integral of tangent cubed x over cosine cubed x. Now, we're not normally, we don't have a strategy to deal with both tangent and cosine in the same problem. We do sines and cosines, or we do tangents and secants. So I think one of the easiest things to do, and I could turn this into sines and cosines, but I think what's easier to do is to move my cosine cubed up top, because remember, if it's cosine cubed on the bottom, then it's secant cubed on top. So then this becomes the integral of tangent cubed x secant cubed x dx. Now we're going to go look at our sheet for our tangent and secants and see if it matches one of the types. If it doesn't, then I would turn it into sines and cosines and see if it matches one of those types. But let's look. So we've got either an even power of secant, which we do not have because it was secant cubed, or we have an odd power of tangent, which we do have because it was tangent cubed. So we're going to do type 2, odd power of tangent, and our first order of business is to pull out a secant tangent. Now we did this on our second set of notes in advanced integration, so this is nothing new, but it'll be a good review over how to deal with this type of integral. So we're going to pull out a secant tangent. So then that gives me the integral of tangent squared x secant squared x, and then remember, when I pull out that secant tangent, we're going to be saving that for our dx. We're going to be saving that for our du. Now, hopefully you've been able to identify which one to replace. So I look at this and I say, okay, if this is my du, then whose derivative is secant tangent? Well, that's secant's derivative. So secant is good. Tangent needs to be replaced. So I'm going to use my Pythagorean identities. And this one is tangent squared plus 1 equals secant squared. Ooh, that's kind of hard to see. So secant squared minus 1 is equal to tangent squared. So that's what I'm going to replace this with. So I'm going to replace it with secant squared x minus 1. And then I have the rest of the integral with my secant squared x and then my secant x tangent x that I'm saving at the back. All right, now we need to do some algebra. So I'm going to distribute my secant squared. So I'll have the integral of secant to the 4th x minus secant squared x. And then I still have my times secant x tangent x dx. And I'm ready for my u sub piece. So I'm going to let my u, let's see, I'll do it in bright pink. I'll let my u be secant x. So my du is equal to secant x tangent x dx. So if I replace, I end up with the integral of u to the 4th minus u squared du. So now I need to do the antiderivative of that, which is 1/5 u to the 5th minus 1/3 u cubed plus c. And then last and final step is to plug in my u expression. So my answer will be 1/5 secant to the 5th x minus 1/3 secant to the 3rd x plus c. Excuse me. All right, so there is my answer for this first one. All right, my second one, let's look, if we look at it, we have x to the 5th plus 1 over x cubed minus 3x squared minus 10x. So if I go back to my integration strategies page, this is a rational function. So the first thing that we have to decide when dealing with a rational function is it bottom heavy or is it top heavy or equal? This one happens to be top heavy or equal, so we have to do long division first. Now the numbers on this problem are terrible. I would never give you a problem like this on a quiz or a test with the numbers this bad. The process is not bad, so yes, I would expect you to do the process. Okay, so we're going to do long division. So we put our denominator outside the radical. And in the numerator, we do our x to the 5th. Now, I put a bunch of placeholders. So 0x to the 4th plus 0x cubed plus 0x squared plus 0x, and then finally our plus 1. Okay, so multiplying, what do we multiply x cubed by to get x to the 5th? So that would be an x squared. Now, remember to distribute. Some of y'all have some weird long division going on. So remember to distribute. So it'll be an x to the 5th minus 3x to the 4th minus 10x cubed. And we are going to subtract. And when we subtract, I like to change my signs. So that goes away. 0 plus 3 makes a 3x to the 4th. 0 plus 10 makes a 10x cubed. And then we bring down our 0x squared. All right, so now what do I multiply by to get 3x to the 4th? And that would be a plus 3x. And here's where my numbers start to get bad. So if I distribute, that gives me 3x to the 4th minus 9x cubed minus 30x squared. And I'm going to subtract. So I'm going to change my signs. So 10 plus 9 makes a 19x cubed. 0 plus 30 makes a 30x squared. And I'm going to bring down my plus 0x. Again, told you my numbers are going to start getting bad because now to get from an x cubed to a 19x cubed, I need to multiply by 19. So this gives me a 19x cubed, and then I end up with a minus 57x squared and a minus 190x. Again, I told you the numbers were bad. So I'm going to distribute my negative. Those cancel out, so that gives me 87x squared plus 190x, and then don't forget you have to bring down that plus 1. Okay, so that is my long division. So now I'm going to turn my integral into the quotient, which is this guy right here, x squared plus 3x plus 19, plus, now I'm going to put my remainder over my original denominator. So it'll be 87x squared plus 190x plus 1 over x cubed minus 3x squared minus 10x dx. Okay, so according to our sheet, we have now done long division. So we're back here and we have all of these options. Well, if I look at the denominator, the first thing I'm going to check for is it factorable? And it is factorable. So if it's factorable, I'm going to use by partial fractions. So I am going to split this up. Well, first I'm going to carry down my x squared plus 3x plus 19. Then I'm going to split this up. This is x times x minus 5 times x plus 2. If you factor it, take a second to make sure you know how to factor that. So it's going to be a over x plus b over x minus 5 plus c over x plus 2 dx. Now, this first part, the quotient, is really easy to integrate. So what we're going to be working on now for a moment is this fractional piece right here. So one of the things that you need to do when working with a 3-term, what a lot of you guys are not getting, is that when I multiply a, if I want to get a common denominator, I have to multiply a by both of the other denominators. So when I set this up, it's going to be a times x minus 5 times x plus 2. He multiplies by both the other denominators. B will be multiplied by x and then x plus 2, the other two denominators. and c will be multiplied by x, and then x minus 5. And then my numerator of my fraction was 87x squared plus 190x plus 1. So that's the equation that I'm going to solve. Now I am going to do the math for you because it is pretty bad. So the first thing that I'm going to do is I'm going to let x be 5 to cancel out the a. So a will cancel out. B will be 5 times 7, so 35b is equal to, if I plug 5 over here, I get 3,126. So that means that doesn't reduce, so B is 3,126 over 35. Told you the numbers were bad, but the process is not too bad. So, okay, so what if I let x be -2? It'll still cancel out the a. It'll also cancel out the b, so -2 times -7 makes positive 14c, and if I plug -2 in over here, I get a -31. So c is equal to -31 over 14. All right, if I let x be, 0 for this one, then a is going to be -5 times 2, which is -10a, equals 1, so a equals -1/10. Okay, so now I'm going to integrate, or I'm going to rewrite my integral. So I'll have x squared plus 3x plus 19. Now I have a is a -1/10 over x. B is 3126 over 35, all over x minus 5. And c is a -31 over 14, that's a 31, all over x plus 2, and then I have my dx. Okay, we've done the hard part. Now we get to do the antiderivative. So x squared goes to 1/3 x cubed, 3x goes to 3/2 x squared, 19 goes to 19x. The first fraction goes to -1/10, natural log absolute value of x. Second fraction goes to 3126 over 35, natural log absolute value of x minus 5. And the last fraction goes to 31 over 14, natural log absolute value of x plus 2. And then, of course, don't forget your plus c. So that is a very long partial fractions problem. Okay, so the next one, or the next two, notice that they involve natural log. So I told you on our sheet that there are two options when involving a natural log. It either contains a 1 over x and we do it as a u sub problem, or it doesn't contain 1 over x and we have to do it by parts. So if I look at this first problem and if I rewrite it, it's really 1 over x square root of natural log of x dx. I like pulling that dx to the side. So you can see that we do have a 1 over x in the problem, so this one is going to be a u sub. So we're going to let u equal natural log of x, so du equals 1 over x dx. And so when I do my u substitution, I end up with 1 over the square root of u du. So that is going to be the integral of u to the -1/2 du, which is equal to 2u to the +1/2 plus c. And then plugging back in my natural log gives me 2 natural log of x to the 1/2 plus c. Notice where my parentheses are. You need to put parentheses around the natural log of x. If you don't, then you're just raising x to the 1/2, and that's not what you're supposed to be doing. All right, on our next one, we do not have a 1 over x, so this one has to be done by parts. Now, the good thing about natural logs is u is always the natural log of x, so both in u substitution and in integration by parts. So we always have a u equals 1 over x and a u equals natural log of x and a du equals 1 over x. That leaves for my dv an x, so v is 1/2 x squared. So going across into the diagonal, we end up with 1/2 x squared natural log of x minus the integral. Now, multiply and simplify these two guys. X squared divided by x is just x. So we get 1/2 x dx. This is definitely an integral that I can integrate, and so my final step is to do 1/2 x squared natural log of x minus 1/4 x squared plus c. Okay, so you only have two options with natural log. It's either u substitution or it's integration by parts. That's it. All right, let's see what the next one brings us. All right, sometimes we need a little bit to get us started. We need a jump start, okay? There's not much to work with, so we need to jump start this problem and see what we can do with what we can do to make this really, frankly, a little bit more complicated. So one of the things we can do is multiply the numerator and the denominator by one of the numerator or the denominator. So in this case, I have just chosen to multiply by 1 minus square root of x on top and on bottom. Now I can do that because that's really just 1 that I'm multiplying by. Also, I could have chosen to multiply by the square root of 1 plus x on top and on bottom. It would have been worked a little bit differently, but ultimately the answer would be the same. So if I do this, then this turns into the integral of, on top, the 1 minus x cancels out. On bottom, the square root cancels out, and I'm left with 1 minus x. In the denominator, my square root doesn't cancel out, but I can FOIL the inside and end up with 1 minus x squared. Now, I put this on our sheet, and I need to add it on, so you may want to add it on. If we have a radical in our problem, a square root, then it's either u sub inverse trig or trig sub. Okay, now we did trig sub last time. We try and avoid trig sub if we can, but this integral can be done with trig sub, but it can also be done in a different way. So if you look at this, when I asked my classes what this looked like, some said, well, I see inverse sine, and I said, okay, but what's the problem? And they said, well, the x is the problem. And then others said, well, I see u sub, and I said, okay, what's stopping you from using that? And they said, well, 1 is the problem. I said, okay, well, what if we pulled it apart? You can do this because we can pull apart our numerator. So we can write this as 1 over the square root of 1 minus x squared dx plus the integral of negative x over the square root of 1 minus x squared dx. So you can break it apart into two integrals because it's the numerator. You cannot ever break apart the denominator with pluses and minuses. Okay, now this guy, hopefully you recognize it as inverse sine, where k is equal to 1 and a is equal to 1, so it integrates to inverse sine of x, okay? Plus, this guy can be done using u sub, so u would be equal to 1 minus x squared, du would be equal to negative 2x dx. We need a negative 2, so we're going to balance it out. Or, well, we need a 2. We don't need a negative 2. We need a positive 2, so we're going to balance it out with a 1/2. So that would be 1/2 the integral of 1 over the square root of u du, which we just did. So this one becomes 1/2 times the integral of u to the negative 1/2 du, which is 1/2 times 2u to the positive 1/2. And so if I plug my u back in and cancel those out, I end up with the square root of 1 minus x squared. I just put it in a square root. Plus, now I have this guy all the way from the front, inverse sine of x. And then I have my plus c. And there you go. If you had worked it out in a different method, you should eventually end up with the same answer. It's just how long does it take you to get there. Okay, what's coming next? All right, on these, we don't have a lot to go on, and I don't really know what fancy form of 1 that I want to multiply by, but it does kind of look like a u substitution problem. Because I have an inside function. My inside function is the square root of x. So I'm going to start like this would be a u substitution problem. So if I let u be square root of x, that at least makes this guy less complicated. But we're also going to have to replace the dx. So if I take the derivative of this like it is, I end up with du equaling 1 over 2 square root x dx. Well, I don't have a 1 over 2 square root x. So what I do in this case is I forego that and I say, okay, let me solve for x. So x would be u squared. And now if I find the derivative of that equation, I have dx outright. I don't have to solve for dx. Now, I would end up getting the same thing if I manipulated this, but this is much easier to work with. So now, if I go replace, then I end up with the integral of e to the u times 2u du. Okay, so take a second, make sure that's sound. You get what we're going. All right, so now I have products of two functions. I've got two functions being multiplied together. Are they related or are they not related? Well, last I checked, e to the u and 2u were not related, so that means we're going to use integration by parts. So remember, on integration by parts, we use our mnemonic device Lipit. Let's see, I'll start with a different color. So according to Lipit, no logs, no inverse trig, but I do have a polynomial. This is my polynomial. So I'm going to let u being 2u, so du is equal to 2. That means dv is equal to e to the u, so the antiderivative is e to the u, and I can go down or across and diagonal. So that turns this integral into 2u e to the u minus the integral of 2 e to the u du. So remember, with by parts, we're hoping we end up with an easier integral to integrate, which we did. So we can now have 2u e to the u minus 2e to the u plus c. And my last and final step is to plug back in my u expression. So it ends up being 2 square root of x e to the square root of x minus 2e to the square root of x plus c. Okay. All right, we're going to do that same trick here with secant squared. We're going to let u be our square root of x and see if we can make this something we can work with. Now again, I do not have a 1 over 2 square root x for this problem, so I solve for x, which is square both sides, and then I can find dx directly, which is 2u du, and I can plug in. So that gives me the integral of secant squared of u times 2u du. Again, two functions being multiplied together, and they are not related. So if they're not related, we're going to use integration by parts. According to Lipit, polynomials comes before regular trig, so u is going to be 2u, du is going to be 2, dv is going to be secant squared u, and the antiderivative of secant squared is tangent. So going across into the diagonal, we end up with 2u tangent of u minus the integral of 2 tangent of u du. Now, we've already done this integral in class. We did it with u substitution. So I have given that integral to you, so the integral of tangent is equal to natural log of the absolute value of secant. So that is definitely an integral that we can do. So we have 2u inverse tangent of u minus 2, and then natural log absolute value of secant of u plus c. So we just took we just took regular tangent and made it natural log of secant. So now I can go back and plug in my square roots. So that would be 2 square root of x inverse tangent square root of x minus 2 natural log absolute value secant square root of x plus c. Never in your wildest dreams would you imagine that that would work out to be secant squared of square root of x. All right. Last ones. Now, a lot of times when I'm trying to make a problem difficult, I really just take a basic problem and I stick in another function and its derivative. So when you see something that's pretty complicated, like these last two, try using a u substitution to get rid of the complicated stuff and make it more of a basic integral. So again, if I have natural log in the problem, the only two options that we have for natural log is, does it contain a 1 over x or not? Well, in this case, it does contain a 1 over x, so we're going to start with u sub. Now, it doesn't mean we might not do something else to finish it, but we're going to start with u sub. So u is equal to natural log of x. Du is 1 over x dx. So this problem turns into 3 over natural log squared would become u squared minus 4u minus 12 du. Now, a lot of you guys want to jump straight to completing the square, but this one actually factors. So check for factoring first, okay? We have a rational function. It is bottom heavy, and the denominator is factorable. So we're going to use partial fractions. So I'm going to rewrite this as the integral of a over u minus 6 plus b over u plus 2 du. And then I'm going to set up my equation, so I'll do it over here. So a times u plus 2 plus b times u minus 6 is equal to our numerator up here, which was 3. So if I let u equal negative 2, oops, there's the bell, then I would get negative 2 minus 6 is negative 8b. We'll let it finish ringing. Negative 8b is equal to 3, so b is equal to negative 3/8. If I let u equal 6, then I would get 6 plus 2 is 8a equals 3. So a equals 3/8. So my integral becomes the integral of 3/8 over u minus 6 plus negative 3/8 over u plus 2 du, which is easy to integrate. That's just our natural log. So that would be 3/8 natural log absolute value of u minus 6 minus 3/8 natural log absolute value of u plus 2 plus c. And then my last and final step would be to plug in. Now, it is kind of weird because we're plugging in a natural log of x, so we're going to have 2 natural log of x's, but that's okay. You're not doing anything with it, you're just writing it. So 3/8 natural log absolute value of natural log of x minus 6 minus 3/8 natural log absolute value of natural log of x plus 2, and then my plus c. And there we go. So we took something that looks really complicated, we did a quick u substitution, and it made it into a problem that was a lot simpler that we could figure out how to evaluate. So that's kind of what the gist is. At least that's how I make problems hard, is I just stick a u substitution problem in there at the beginning. So take a second and look at this one. We have negative 4 cosecant x cotangent x times divided by the square root of 9 minus cosecant squared x. Now, I look at this and I say, okay, I know I got lots of inside functions, outside functions. I got a lot going on. But I look at cosecant and its derivative, negative cosecant cotangent. So right away I see, you know what, those guys are related. So let me pull those out of the problem by doing a u sub. So I'm going to let u be cosecant of x, and I'm going to let du be a negative cosecant of x cotangent of x dx. Now I'm going to rewrite this problem and separate it so that it's 4 times negative cosecant x cotangent x divided by the square root of 9 minus, and then I'm going to write it as cosecant x squared dx. Okay, so when I go do my substitution, this is all my du and this is my u. So I end up with the integral of 4 over the square root of 9 minus u squared du. Now, let's go back to our u substitution for a moment, because a lot of people try and tell me that u should be cosecant squared. Well, if u is cosecant squared, then that gets into the chain rule, and our derivative would be 2 cosecant x times a negative cosecant x cotangent x. And it's got extra stuff. We don't have that 2 cosecant x. All we have is the negative cosecant cotangent. So if it's simple, we can just remove the squared from the inside function, and then it becomes just a plain old derivative, okay? All right, so from here, hopefully you recognize this as an inverse sine. So k is equal to 4 and a is equal to 3. So this integrates to 4 inverse sine of u over 3 plus c. And then if I go back and I plug in my cosecant for my u, I get 4 inverse sine of cosecant x over 3 plus c. And there we go. So again, using that u substitution to reduce the integral into something that's in simpler form, and then plugging the u substitution and plugging the u back in after you've integrated it. All right, I hope that helps. We will continue integration in our next lesson. Bye, guys.